Hello, welcome back to Engineering Circuit Analysis. This is a really interesting problem, and I'll explain why here in just a second. First of all, it looks like a non-inverting amplifier because we're driving the input into the non-inverting terminal. We have our traditional feedback and RS resistance there. We have an output resistance. We're trying to find out what this output voltage is given everything else in the circuit. But the thing that makes it interesting is that we actually have two sources. We have 0.4 volts driven through a 27 kilo ohm resistor, and we have 0.8 volts driven through a 13 kilo ohm resistor. Now at first glance, this kind of looks sort of reminiscent to the summing amplifiers that we did in the non-inverting amplifier case. Way back, we did that several lessons ago. Because basically you're driving the input, but you're driving kind of two things in parallel, two voltages in parallel with two different resistances and so on. So a lot of students at first are going to try to treat this as a straight non-inverting summing amplifier. And if you know how to do that, you can, but the problem is that we haven't done any analysis of this. So I have never drawn this configuration with these two sources driven by different resistances and done an analysis of it to show you how to handle it. So a lot of times you'll try to take what you've learned in the past and kind of force it into what you have, but because you're trying to look for a quick way to do the problem. But in reality, that ends up getting you into trouble because this configuration is different. You're driving it down through a different terminal, you have a different gain equation, you have a bunch of other things going on. So resist that urge. Unless you have a derivation or a proof of a non-inverting summer in front of you and you know how to handle it, then you're going to have to ultimately go back to first principles to solve the problem. Now I'm going to make a confession to you here. When I did this, I solved it a totally different way than you probably were going to think to solve it. I used first principles. I did a bunch of node voltage equations and I solved what the output voltage was here because when I first looked at the problem, I didn't really, well, there are different ways to do it. It's just that that was my first gut because I never had a configuration quite like this that I presented to you. So because I couldn't put it into the right form or I didn't have anything ready that I had already done an analysis of, I went back to first principles. That's how I'm going to solve the problem for you here in just a second. But then as I started to record this lesson, I looked at it and I said, well, wait a minute, there's a much easier way to solve this problem. I'm not going to tell you what it is yet. I hope that you see it. You should be able to see it. And if you do, excellent for you. But what I'm going to do, what I've decided to do, instead of trashing my work, I'm going to work it for you both ways because this kind of thing happens a lot. You look at a problem and you don't see it for lack of a better word, you don't see the quick and easy way to do it. So I'm going to show you how to roll up your sleeves and jump into it and get an answer, right? Using a totally different method. And then sometimes you look at a problem and you say, oh, well, that's trivial. This is exactly how you do it. And I'm going to show you how to get the exact same answers in like 1/3 of the steps. So first, let me show you my initial